We're going to continue in section 2.2 with evaluating limits algebraically. And now we're going to look at limits at infinity dealing with rational functions. Say we're asked to evaluate the limit as x approaches infinity of 6x minus 5 over 2x plus 3. Now, I'm going to show you the algebra involved to evaluate this limit. And then for this question, we're going to be able to develop a shortcut rule. So the rules is, when I'm doing limits as x approaches infinity or negative infinity of a rational function, I'm going to multiply by 1 over the highest power in the denominator. So the highest power in the denominator is x. So I'm multiplying the bottom by 1 over x and the numerator by 1 over x. So this is going to be the limit as x approaches infinity. 1 over x times 6x is going to be 6. And negative 5 times 1 over x is going to be negative 5 over x. 2x times 1 over x is going to be 2. And 3 times 1 over x is going to be 3 over x. Now, if we think about this, if I have a very large number placed down here for x, and I divide that into a constant, that is going to be so small and negligible, we're going to say that that's going to be 0. So those are eliminated, and all I'm left with is 6 divided by 2, which is going to be a limit of 3. And this 3 is really the equation of my horizontal asymptote that this graph would approach. Now, take a look back at the original question and see if there's a relationship of how we can come up with a value of 3. Well, I'm hoping some of you see that 6 divided by 2 is equal to 3. And yes, that is true. And the only way we can use this rule is if the degree of the top, which in this case is 1, is the same as the degree of the denominator. So if the degree of the numerator and the denominator are the same within a rational function, I can simply divide the coefficients in front of those powers to get my answer. So basically, there is the rule. So if you want to copy that down, maybe pause the video, you can do that. And there is the rule if the degree of the numerator and denominator are the same. Okay, so in dealing with this question here, now that we know the rule, I see the degrees are the same. My number in front here is 1. 1 divided by 2 down here is going to be 1/2, and I am done. And again, that means my horizontal asymptote as x goes to the left would be 1/2. Okay, what happens now when the degree of the top is bigger? Well, let's develop a second rule. And again, I'll go through the same procedure. I'm going to multiply by 1 over the highest power in the denominator. And in the top, I'm going to get this is equal to the limit as x approaches infinity. Well, x times 1 over x squared is going to end up being 1 over x plus 7 times 1 over x squared is going to be 7 over x squared. 2x squared times 1 over x squared is going to be 2. 3x times 1 over x squared would be 3 over x. And minus 1 times 1 over x squared would be minus 1 over x squared. Again, anything that has a constant over x and x is going to infinity or negative infinity, that's going to be a 0. 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 So I'm left with 0 over 2, which is 0. So if the limit of the degree, of the top is smaller than the degree of the bottom, and my limit is going to infinity or negative infinity, the answer is going to be 0. So again, you can pause the video and copy down that rule if you wish. Now in the last case, we have the degree of the top is bigger than the degree of the bottom, and again, we'll go through the same algebra. So I have 1 over x times 1 over x, and this is going to equal the limit as x approaches infinity. This is going to be x plus 5 all over 1 minus 5 over x. Again, this term would be 0. And now if I substitute a large number in for x and add 5, divide by 1, I'm going to get a large number, and that large number is going to be positive infinity. Had this been going to negative infinity, I would have been substituting in a large negative number here, plus 5 is still a large negative number, divided by 1, the answer would have been negative infinity. So what this means is as my graph goes further and further to the right, my y values or my graph is going further and further up, okay? And if the degree of the top is bigger than the degree of the bottom by 1, I'm actually going to have an oblique asymptote. So I'm going to have an asymptote that's going to be at an angle, and my graph would be going off up like this or down like this towards the asymptote as it goes to infinity or negative infinity. So the rule is right there. The degree of the numerator is greater than the degree of the denominator. The limit will either be positive or negative infinity. And again, you can, if you graph this equation on Desmos, you'll see a nice relationship of what the oblique asymptote would look like. All right, now in the next section, we're dealing with finding limits at infinity of functions containing radicals. So these functions are no longer rationals because the top is not a polynomial. This is an algebraic function. So I'm going to show you another procedure to evaluate these limits. Okay, and the first thing I'm going to do is I'm going to factor out under the root sign the highest power. And the highest power I have is x squared. So if I factor in x squared out of the top, I'll be left with 25 plus 3 over x. And I'm going to factor the largest power out of the bottom, which is an x. This is going to give me 6 over x minus 1. And why do I do that? Well, again, this term and this term will become 0. So this is left to be the limit as x approaches infinity of the square root of 25x squared over x times negative 1, which is going to be negative x. Now, here's where we have to be careful. Okay? In the numerator, I could continue and say this is the limit as x approaches infinity. The square root of 25 is 5, and I'm just going to leave that as the root of x squared right now, and this is still over negative x. Now, some people will say, well, the square root of x squared is simply x, but that is not necessarily the case. The square root of x squared, by definition, is the absolute value of x. And the absolute value of x is x if x is greater than or equal to 0, and negative x if x is less than 0. So the first thing I'm going to do is I'm going to rewrite this and say this is the limit as x approaches infinity of 5 absolute value of x over negative x. And now I have to get rid of my absolute value by either using the positive branch or the negative branch. And how do I determine that? Well, my x values are going to positive infinity, which are greater than 0. So I'm going to replace my absolute value of x with positive x because my x values are greater than 0. So this is going to be 5 times x over negative x. If you simplify that expression, you'll get negative 5. So that means as I go to the right, the limit as x approaches infinity would be negative 5. So my horizontal asymptote to the right would be negative 5. Now, if this limit in the question was the same, but the limit was as x goes to negative infinity, everything up until this step would be exactly the same. I would have the limit as x goes to negative infinity of 5 over the absolute of x divided by negative x. Now, in this case, because x is going to negative infinity, that's less than 0, I'm going to replace the absolute value with negative x. So this is going to be the limit as x approaches negative infinity of 5 times negative x over negative x. And now those would cancel, and now my limit would be 5. So this means as the graph goes further and further to the left, the graph is approaching 5. So I actually have 2 different horizontal asymptotes, one going to the right and one going to the left. All right, I want you to pause the video and give this one a try. Okay, hopefully you had a chance to try it. So this is going to be the limit as x approaches negative infinity. And I'm going to factor out an x squared. So I'm going to get 16 minus 7 over x squared. I'm going to factor out an x and get 1 plus 5 over x. Again, this is 0, this is 0. So I'll be left with the limit as x goes to negative infinity of the square root of 16x squared over x, which is going to be the limit as x goes to negative infinity. The square root of 16 is 4. The square root of x squared is absolute x. And now I'm going to determine what is going in place of, that's a negative infinity. What's going in place of absolute x? Well, because x is going to negative infinity, I'm going to be using the negative branch. So now I have negative 4x over x, which is going to result in negative 4. Okay, the last part of this section is dealing with limits involving absolute value. Okay, so when we deal with limits involving absolute value, we first of all have to get rid of the absolute value sign, just like we did when we took the square root of x squared. So the first thing I need to do is I am going to figure out, okay, if I approach, well, first of all, when I deal with an absolute value, you have to remember that there are two cases again, because the absolute value of z minus 3 is either z minus 3 or the negative of z minus 3, depending on the domain. Okay, so again, let's figure out that domain. So I know z minus 3, if I take that out of the absolute value sign, the 0 would be 3. If I take a number to the right of 3, like 4, it makes z minus 3 positive. 2 makes it negative. So if the number is greater than 3, so 3 to infinity, I'm going to use z minus 3. If it's negative infinity to 3, I'm going to use negative z minus 3. Well, I'm approaching 3 from the left, which is this side, so that is negative. So that means to get rid of the absolute value sign in this equation, I have to use the negative branch. So this is going to be the limit as x approaches 3 from the negative side of z minus 3. And to get rid of the absolute value sign, we said we're using the negative branch. So these are going to cancel. I'm left with 1 over negative 1. This answer is going to be negative 1. So again, when you're doing limits involving absolute value, you need to get rid of the absolute value sign and determine whether you use the positive branch of whatever is inside or the negative branch. Let's take a look at question B. So now I have the limit as x approaches negative 2 from the right of x squared plus 3x plus 2. Okay, well, we know that that numerator, just to make our math a little easier, can be factored into x plus 2, x plus 1. And that's still in the absolute value signs all over x plus 2. So again, I want to know the limit as x approaches negative 2 from the left. So let's take whatever's inside my absolute value sign, and let's place it on the number line. So negative 2, negative 1. Okay, and as I approach negative 2, let's put in a negative 3 here. Negative 1.5 and 0. Negative 3 is negative, negative. That's going to be positive. Negative 1.5 is positive, negative. 0 is positive, positive. Okay, so now as I'm approaching negative 2 from the left, so here's negative 2 from the left, it's positive. So I'm using the positive branch of this absolute value. So that means I'm just going to replace, whoops, that should be the limit as x approaches. It's the limit as x approaches negative 2 from the left. And we said we're using the positive branch. So I can remove the absolute value sign and just use the positive of x plus 1 times x plus 2. And like before now, the x plus 2's cancel. I substitute a negative 2 in for x and get negative 2 plus 1. So this answer is negative 1. All right, so there's your assignment on limits involving infinity and limits involving absolute value. So give those a try. If you have any questions, the answers are on the website.